So let's talk colors. All right, we said that white light is all the colors, but really, we have found that there are three colors that when you combine those three colors or three frequencies of light in varying intensities, that you can get interference that lets the brain perceive every color. And so those colors are called the primary colors of light. Now, you may know from art class what you think the primary colors are, but the artist's primary colors are different than what the physicist's primary colors are because our definition is different for those. So what are the primary colors of light? Well, two of them we're going to definitely agree on, and those are going to be red and blue. Primary red, primary blue. But the third one, the artists say, is yellow. What we're going to say is the primary color of light. Third is green. Okay? So red, blue, and green are the primary colors of light. And actually, you probably have experience with that. If you think about your computer and you have wires going into your computer, what are the names of those wires going from, say, from your DVR to your television? And they're the RBG colors. An old-fashioned television before the liquid LCD TVs or the HD TVs, if you looked really close to them, they had pixels. And what were the colors of the pixels? They were red, blue, and green. Because we've always understood that if you create varying intensities of red, blue, and green, you could create any color. Those are the primary colors of light. The secondary colors of light occur when you mix two primary colors at equal intensity. Now I'm going to show you some stuff a little bit on a Screencastify that goes through this so you can see it as well as, or actually probably have you do an activity with something rather than me doing it as a Screencastify to tell you the truth. So let's talk about what you get. Red plus blue, right? Red plus green, blue plus green. So red and blue, what do you get when you mix equal intensities red and blue? Some people are going to want to say violet. It's not really violet. It's kind of a violet-esque shade, but the formal name for what you get when you mix primary red and primary blue is a color that you might know, magenta. Magenta, okay? And you'll see this on that demonstration. It's sort of like it is purplish, but it's not classically purple. I was going to go down here to blue and green. What do you get when you mix blue and green? Some people are going to want to say things like teal or aqua, but the right answer is actually a color that is called cyan, and you'll see that color. Green plus red, this is the one that people don't ever believe, but you actually do get yellow, okay? I'll find a video which will demonstrate this to you, right? Magenta, yellow, and cyan are the secondary colors of light. Now you may know magenta, yellow, and cyan from a different place. And if what you're thinking is your printer, your color printer if you have one, your color cartridges are magenta, yellow, and cyan. Hold on to that, that's gonna become important. Now, what we're gonna talk about next is what are called complementary colors. Different definition than the art definition of that. This is two colors at equal intensity that make white light. And so if we're going to say that red plus blue plus green equals white light, the complementary colors then are magenta, right, which is red and blue, plus green. Yellow, which is red and green, plus blue. Cyan, which is blue and green, plus red. And those are your complementary colors. When you add them together or you have equal intensities of them, you do get white light. Now, where can we demonstrate this? Well, anyone who's been to the theater, if you ever look up at the lights It's never just white light. There's always a gel in front of that light to turn it a color. And what colors do we tend to use for gels? We tend to use red, blues, and greens. You never light a stage with white light. Everyone looks pasty and sickly when you do that. You have red, then blue, then green, red, then blue, then green, red, then blue, then green, and that creates a nice white light that covers the stage. Now, that's not what happens with this, because these are talking about sources of light, like a red laser, a yellow laser, a blue laser, or something with a white light that has a blue filter in front of it such that I get blue light. This is not its own source of light. It is not luminous. It is being illuminated. So something is making me see red here. And remember what we said, that white light is hitting this. Everything except for red is being absorbed, and red is what's being reflected. So what is the thing that's doing the absorption? Well, that thing is called a pigment. A pigment is a molecule or chemical that absorbs specific frequencies of light and reflects all else. So what does that sound like? And if you said resonance, you're right. It's that the structure of that molecule resonates with specific frequencies, absorbing them, and reflects all the rest. So what's going on there? Well, we're going to have things that are called primary pigments. And a primary pigment is going to be a pigment that absorbs one primary color. So in other words, there's going to be a primary pigment that will absorb red, that will absorb green, that will absorb yellow. So if I absorb red, that means what's being reflected. What's being reflected out of the white light is everything that's not red, not green, this should be blue, right? What's being reflected, if it's not red, the green plus the blue is being reflected. And so what is that? We see that as a cyan thing. So a cyan pigment absorbs red, reflects green and blue, which is why I see green and blue. If I absorb green, then I'm reflecting or reflected red plus blue. And if I reflect red plus blue, that means red plus blue is getting to my eye. I see magenta. And then blue then must reflect red plus green, and I must see that as yellow. And that is why, folks, the color cartridges in your printer are cyan, magenta, and yellow. They are absorbing each one of the primary colors of light, which is why it can some combination of cyan plus magenta plus yellow ink can create every color, because it absorbs specific portions of the red, green, and blue, so that specific amounts of red, green, and blue are getting to your eye to create all the other colors. So there you go. A secondary pigment, well, hopefully you can see what the definition is. It is one that absorbs two primary colors of light, right? So we're going to have one that's going to absorb red plus green, absorb red plus blue, absorb blue plus green. So if I absorb red plus green, it must be reflecting blue, which means I see blue. Red plus blue, that must reflect green, therefore I see green. And then blue plus green, it must reflect red, therefore I see red. So that's what's going on. The blue, green, and red are secondary pigments because they're absorbing the other primary colors of light. Therefore, what happens if you have something that absorbs red plus blue plus green? What do we see? Well, what we see is black, and that's what black is. So, have you ever noticed that if you run out of black ink in your printer and you let it use the cyan, magenta, and yellow, that you use a lot of it? Well, that's why, because you have to use a lot of ink just to get the black, rather than just using black ink, which is one pigment that absorbs all those colors, rather than three separate pigments that are each absorbing one of the colors. And that is the color theory of light when we're talking about reflection. But let's talk about some interesting applications. So has anyone ever been in a dark room? A dark room where photography happens usually has red light in it. So that means the light bulb only emits red light. It's not laser light, it's not coherent, it's not intense, but it's just got a filter over the light bulb that does that. If I'm wearing a blue shirt in a dark room, what do I see? Well, that blue shirt, when I'm saying that, that's saying that the pigment is blue. If we look back, what does a blue pigment do? A blue pigment absorbs red plus green. And the only thing that's in this room is red light, but this blue pigment is absorbing all the red light that hits it. So what do? This shirt looks black, right? Because literally nothing is getting reflected to our eye, and the way that our brain perceives a lack of light is black. Let's go another example. Let's say in a room I have a cyan light bulb, right? And I'm wearing a, I don't know, magenta shirt. Not that I ever would, because that would look awful on me, right? My coloring is not right for that, but there you go. So cyan light bulb. So if it's cyan, what type of light is in the room? Well, cyan is blue plus green light. So that's what exists in the room. What does the magenta pigment do? A magenta pigment absorbs green and reflects red plus blue. So in this room, there's blue and green light. This magenta pigment is going to absorb the green light and reflect the blue. It can't reflect red because there's no red light in the room. Therefore, that cyan t-shirt, or excuse me, that magenta shirt would in that room look blue because blue light is being reflected. And so we could do some sort of interesting problems with this in terms of figuring out what color lights are there in a place, what types of pigments are there in the place, and what do we see. So some examples of the color theory of light.